start with new topic. So first thing, I will share my screen. Let's see which screen, not this one. Which one? Not this one. Oh, okay. Yeah. So today we will start with a new topic, a new learning algorithm. So it's called the K nearest neighbors. So this is a new one. Last class, what we learned is decision tree and random forest. And this is different. This is called K nearest neighbors. Okay. And the major different thing for this one, so of the above we learned, they are supervised. And K nearest neighbors, it belongs to unsupervised learning approach. Okay, so it's unsupervised. And it also belongs to clustering. Okay, so what's the concept of this? So the complete name we already mentioned is called K nearest neighbor. So based on the name, you can figure out it's kind of try to find the nearest neighbor, etc. And normally K means K number. And the abbreviation for this learning algorithm is called KNN. And it says it is a lazy learner. Okay, and why we say it's a lazy learner is because it doesn't learn a discriminative function from the training data, but instead to memorize the training data set. Okay, and if you recall in our previous discussions, like SVM or logistic regression or perceptron, a stochastic a gradient descent of those, it's involved with some discriminative function from the learning data. So you need to optimize the weight. So that's the learning goal. And compare with those, KNN doesn't need a discriminative function. Okay, so that's why we say it's a lazy learner. The algorithm itself, it's very easy to understand. Okay, so let's see. So the algorithm, it says you need to choose number of the K. So that will be your cluster size. And you also need to choose a distance metric. Okay, later on we are going to discuss what is distance metric. And then you find the K nearest neighbors of the sample that you want to classify. Okay, and then you assign the class label by a majority vote. So the algorithm itself, you can see it's quite simpler. It doesn't involve a lot of math derivation. So that's why we call it a lazy learner. So let's see diagram to understand what all of this means. So this question mark one, so this is the sample you want to clarify. It belongs to which class, red class or blue class or something like that belongs to, so you want to categorize to which class. So with KNN, what it means is, so in this case, we choose K as 5. So you're going to choose 5 neighbors, okay, of this sample. And among these 5 neighbors, so in this case, we have 3 classes. We have triangle class, we have circle class, and we also have the plus class. So among this 5 nearest neighbors, so you can see it's kind of like a cluster. So you pick these 5 nearest neighbors among all of the neighbors that's nearest to the sample that you pick. So for this question mark one, then in this cluster, so it's very obvious in this case, the triangle class takes the majority. So that's why we see it follows majority voting. Okay, so the majority voting is triangle class. Then we will say, okay, so this sample we predict it's also triangle class. So this is what the idea about k-nearest neighbor learning algorithm. Okay. So we understand the concept of k-nearest neighbor. So next, let's see its advantage and disadvantage. So the main advantage of it is such a memory-based approach. So this is memory-based approach compare what we learned before. Is it what we learned before, especially some of the algorithm, you can apply it, we call it online learning algorithm. So with online, you don't need to load all of the data in memory. So you can learn on demand. So we call it stochastic gradient descent. This way, it's a memory-based approach. Okay, so the classifier immediately adapts as you collect new training data. So it can adapt whenever you collect the new training data, okay? And the downside for it is that the computational complexity for classifying new samples, it will grow linearly when the number of samples grows, is it? And also when the number of samples has very few dimensions, is it? So the features, the limited feature, okay. And the algorithm has been implemented, okay, using like efficient structures. So that's the downside of its computation complexity, okay. And furthermore, it says we cannot discard training samples because no training step is involved in this case. Okay, so the storage space can become a challenge when we work with a larger data set because it's a memory based. So it has its advantage, but it also has its downside because of the memory based, because you need to have all of them loaded. So the storage space can be a challenge. Okay, so that's the advantage and the disadvantage. And some other important thing we need to look is the neighbor. So then the number of choice of the neighbor is also crucial, is it? So you need to find a good balance between overfitting and underfitting. You don't want to choose too many or too few. So what's the right choice of the number of neighbors? So that's crucial. And also the distance matrix, is it? So what will be the best distance matrix? The distance matrix, when you pick it, needed to be appropriate to the features in the data set, is it? Yeah, so those two are also crucial. And regarding the distance matrix, generally speaking, that the distance matrix we always hear is like Euclidean distance matrix, is it, for real value samples, okay? And but just remember, when you use Euclidean distance measure, remember to standardize the data. So previously, we also learned that even when we do gradient descent, when we do SVM or perceptron, etc., and what we call as feature scaling. Okay, so you also need to do feature scaling, basically, even in this case. So feature scaling. And one of the approach to do feature scaling is you can standardize your data, okay, so that they contribute equally to the distance. But because otherwise, if you don't do this, it's very hard to see how the distance is going to impact. Okay, then regarding the distance, so let's take a look at the definition of distance. And generally speaking, there is a definition for the distance. It's called Minkowski distance. Okay, it's a Minkowski distance is a generalization of Euclidean and Manhattan distance, and its expression is something like this. Okay, so it's the coordinates difference, is it 2 to the p power, and then you can do the 1 over p of the power again. So let's see. The Euclidean impedance, if the p is 1 or 2, what is this? Is it? So when p is 2, it's Euclidean distance. When p is 1, then it's Manhattan distance. Okay. And this has many other distance metrics also available in sklearn. So sklearn, that package we already know, we already used quite often. Okay, and it's provided within that package about other different of distance matrix. And if you want, you can take a look. And over here, what we are going to see is one of this is Euclidean or Manhattan. Okay. And next, let's see some more discussions about the KNN. It says KNN is susceptible to overfitting, okay? And susceptible to this overfitting, why? It said due to the curse of dimensionality, okay? So what is the curse of dimensionality? Curse of dimensionality, so the definition of this curse of dimensionality, so the definition of the curse of dimensionality is it describes some scenario, the feature space is as it becomes increasingly sparse for an increasing number of dimensions of a fixed size, the training data set. Okay, so your feature space is kind of as become increasingly sparse when the number of dimensions increase. Okay, so this is your called curse of dimensionality. Okay, and how we understand this scenario is we can think of as even the closest neighbors being too far away in a high dimensional space to give a good estimation. So it's just that it's because the critical point of the k-nearest is a cluster. It's one of the clustering algorithm, is it? And if it's a clustering algorithm, so if your data is kind of clustering, then it's easy to group, is it? But if because of the feature separate them too further away, then the meaning of the closest neighbor is that it just become too further away. So it's kind of a contradiction here. And the regularization in regression that can avoid overfitting. Previously we learned the regularization concept. So it's that special C term. That when we learn SVM, when we call the sklearn module, so that's parameter is considered regularization. And the purpose for regularization is try to penalize weight. Penalize weight. You don't want a certain weight to take too much of the share, So you add another term in your cost function because your overall purpose is to minimize the cost function. When we discussed previously, the cost function. So if you add this term, you're going to add some of this term, Then of course you can penalize the weight, okay? So that's the general idea about regularization to avoid overfitting, okay, overfitting. But here it says regularization is not applicable, Is it? Because why? For decision tree and for KNN, is it? Because both of they don't have any uh, like what we said, the cost function, is it? So you cannot do that, especially with KNN. There is no discriminative function involved, is it? Just based on the clustering, is it? So then in this case, how do we avoid overfitting, is it? So there is another way to do to avoid overfitting is we use feature selection and dimensionality reduction. So those are also some techniques, okay? So just remember in machine learning, there are different techniques to deal with overfitting or underfitting, is it? So over here with KNN, then feature selection, you don't choose regularization, okay? You choose feature selection or you choose dimensionality reduction, okay? Then it can help us to avoid what we call the curse of dimensionality issue, okay? So that's the approach for KNN to avoid overfitting. Later on, we will see that. And here it gives more discussion about KNN. So KNN, it compute distance between points, is it? And then it pick a most popular class of the top K classes of points nearest to it. So that's the idea. And the distance calculation, you can use Euclidean distance. And also it says the number of nearest neighbors, is it? What's the optimum number, is it? And says it should be greater than the number of the groups, is it? So if you choose the number of nearest neighbor less than the number of groups, that's not a good choice, is it? And the downside is that it's in scale and with outliers and bad data. That's a downside for KNN. Is it? And why we said in scale? In scale, because you need to compare data in question to all of the points from the data set. Is it? Before you can choose the closest points. Is it? That's why it performs slower and slower when you have more data. Is it? If you have huge amount of data, and each time when you do some sample, you want to check which class it is. And so you need to compare all of the points, is it, for the distance, and then you find the closest number of the points. So that's why when you have more data, the more data you have, the slower it is for the calculation. And in order to solve the problem is that you can use parallel processing to speed up, okay? And parallel processing, I remember last class when we discussed decision tree and random forest, we also mentioned that. So one of the option in sklearn is you can specify the option for the parameter, we call it n jobs, okay? So you can specify the n job to some number, like 100. Then in this case, it will run 100 operations at the same time, so that even if you have some huge data, it can expedite your processing. Okay, and then the next one, let's see, we are going to do some quick comparison, because we already learned a number of algorithms, is it? And for different scenarios, you can pick a different learning algorithm. And also we know there is some linear question and some non-linear question. So just remember, for questions, not all linear. Some of them it's also non-linear, okay? So if you care a lot about interpretability, is it, you want to know white box instead of black box learning, is it? Then you can use decision tree, is it? Because you can see a lot of internal working mechanism, is it? So that's about decision tree. And logistic regression, we also learned. Is it logistic regression? It's all, you can also do online learning for logistic regression through what? Through what we previously learned, stochastic gradient descent. Okay, that's the online one. And one nice thing of logistic regression compared with other similar one, the classification is it can predict, not just predict, with the probability of your prediction. So it will also give you out the probability of the prediction. Okay, so that's a nice thing. And the next one, what we learned is support vector machine, SVM. Okay, so it's quite good for linear models. We already see, is it? But with kernel trick, so you can apply certain special function, is it, to increase the dimension, is it? So in that case, it's not a decrease, increase the dimension to convert your problem from lower dimension questions to higher dimension questions, is it? And then you can extend it to linear, non-linear problems. Non-linear problems, okay, and then you can use some plane, some curve plane, is it, to separate the data, and we discuss some of the examples also. And we also learn random forest, and random forest belongs to ensemble method, okay, ensemble. And why we say it belongs to ensemble is because it uses the average of multiple decision trees, is it? And you don't need to worry parameter tuning, okay, to avoid the overfitting. And you average, so you will have a number of the trees, is it? And then you average them, you find the result. So that's the idea for random forest. And the KNN, that's what we just learned. So KNN is unsupervised. Okay, so remember it's unsupervised learning. Okay, so, and it's lazy learning, we also say, because you don't need to know any primitive functions, is it? So it says it's allowed to make a prediction without any model training, is it? Because it's unsupervised, is it? It's based on clustering, but the computation is expensive. Okay, it's expensive. So that's the overall comparison among the algorithms that we already discussed. Then next, what we are going to discuss is another concept in this chapter. I believe it's called data preprocessing, okay. Yeah, so the next concept we need to discuss is data preprocessing, because we are going to see it's also used a lot when we do machine learning, is it? And we already learned before, is it, to deal with missing data, is it? And today we're also going to see how do we deal with categorical data, because machine learning, it need a number. Okay, a lot of math functions, they need a number. They cannot just use string to do its calculation. So how do we convert that? Okay, and the third thing is because of the curse of the dimensionality, is it, the overfitting issue, is it? Sometimes you cannot use regularization to solve the problem, is it? So then in that case, you need to select the relevant feature. So how do we achieve this? Select relevant features. So these are the discussing point. To deal with missing data, previously we learned some pandas method, like functions drop n, a fill n, a, etc. So you can do that, okay. And we are also going later on, take a look the example, like the imputer from sklearn, okay, how to do that. And deal with missing data over here says you can remove of the missing data, is it? But in that case, you are going to reduce the number of your samples, is it? maybe you remove too many samples. Then when you do training, it's not a good idea, is it? So a lot of time, we can choose some other way. So to deal with missing data, so instead of you remove it, is it? And we can do interpolation of the missing data. So you substitute the missing data with some other thing. And a lot of time we use what we call its mean imputation. So you fill the missing value with mean value of the entire feature column. Okay, so a lot of time you borrow this approach to impute, we call it impute missing value, okay? And later on in our code, we will see in sklearn, we have the estimator, okay, API, okay, estimator. And it's quite useful, is it? And over here it shows us, so you can use training data and the training label, as it you do fit, and you have the model, as it, and then you can apply the testing and then do prediction. Okay, so that's the procedure that we follow. The next topic is about the categorical data. For categorical data, generally, we have the two different types. We have nominal and we have ordinal features. Okay, so what are those two? How do we deal with that? Is it? And ordinal means they can be sorted or ordered. Is it? Like over here, example, t-shirt size. Is it? It is given as like XL, L, or M, but they can be ordered, they can be sorted, is it? So this is one category. Another category is a nominal, is it? So nominal, it doesn't have any order, is it? Like the t-shirt color, red, blue, or green, is it? Those don't have order. Then how do we deal with all of this situations? How do we deal with nominal? How do we deal with ordinal, is it? So we need to do some processing, okay. So let's see. Here for ordinal, we can do some mapping. Okay, we can do some mapping, and you can use a label encoder model to deal with it. Okay, so class label is encoded, then going to be as integer values. Okay, so this is easy to understand, is it? And for nominal, okay, for nominal, how do we deal with it? So here is a concept you will see a lot in machine learning. We call it one-hot encoding. Okay, one-hot encoding. So this is a term, and it's a frequently used technique in machine learning. So what this means is, it means it's going to create a new dummy feature for each unique value in the nominal feature column. Okay, so in pandas, you can achieve this through a specific method called getDummies, and we will see that. Okay, and you can also do some other way with sklearn's pre-processing module, one-hot encoder. Okay, so the idea, suppose you have the color column. So this is a column, and within the column you have red color, you have blue color, and you have green color, is it? So those are not ordered. So how are you going to assign value to them? Is it assign 1, assign 1,000? Is it? Doesn't make sense a lot of time, is it? So what it's going to do is that one-hot encoding. So what it's going to do is it will convert it to 3 columns correspondingly. So R, red, blue, and green. Okay, and then it will, so if it is red, then you put 1, and for all of the remaining you put 0. That means for this sample, so this is a sample. So the rows are samples, is it? And because it's red color, so that's why you only, it's called one hot. So you only apply this one to this specific value. And for this one, then it's not red, but it's blue. So you code blue as 1 and green is not. So you put it as 0, okay? And same thing for the last one, then green is encoded as 1. So then in this case, you convert from 1 column to 3 column. Okay, so basically it's kind of you add 3 more features, is it? Instead of you only has 1 feature called column, then you have 3 features called red, blue, and green, is it? So that's what, but you do then have the value, is it? You have number, numeric value. Then if you want to apply it to SVM, to logistic regression of those, then you have the values to deal with it. So that's the idea of one hot encoding, okay? And it can be achieved using get dummies. And later on, we will see in our coding. And what the next, basically, previously we already, I believe in all of our examples and your assignment, you already did that. Is it automatically call that train test split function to split your sample space into training data set and testing data set. So we already know that. And this one, I believe we also cover. So just a quick review, is it? So to feature scaling, so this is the scale of your feature, is it? And we have 2 ways. You either do normalization or do standardization, is it? So normalization, you use minimum and maximum scaling, okay, like this formula games, is it? So then it will scale, rescale of your feature to all of them to this range, etc. So that's called normalization. The second way we call it called standardization, is it? And standardization, it uses the mean value and the standard deviation, is it? It's use variance and the mean, okay? So that you can standardize a value. So that's the second way. And we also apply those in our previous examples and your assignments. And over here discuss, because of the overfitting problem, is it? How do we select meaningful features, is it? And what can cause the overfitting? Overfitting is that because the model fits parameter too closely, is it? With the training data set, is it? With the training data. So one of the reasons for the overfitting is because model may be too complex. Is it? Like previously we say, if you have all of the points, is it? And for some reason your model just exactly follow that, then it's going to be overfitting, because next time when you have a sample you want to predict, then in this case, then it doesn't work, is it? So this called your model is too complex for the training data, is it? So how do we solve this issue? Is you can have more training data, is it? So that's one way to solve the issue. The second way is through the regularization to do the penalty, is it? That's what we said, that's a C parameter. Is it? And for this one, you're going to, because of the C, you are going to lessen the weight impact, is it? So that's the second way, we call it regularization, so generally. Okay, and the third one is you get your model not that too complex, is it? You choose a more simpler model. So like in our previous discussed case, is it? You don't pick like this kind of model, is it? So what you pick is you can pick like something like this, is it? So Then if we pick this model, then compare with the other one, it's much simpler, etc. So with fewer parameters. Okay, so that's it. And one other approach is you reduce the dimensionality of the data, etc. So reduce dimensionality of the data, so that means you don't pick so many features, etc. You just pick whatever the most important features that are going to impact your model. So that's the general idea. And over here it says common way to reduce overfitting is by regularization. So regularization used a lot, is it? And the other one is called dimensionality reduction. Okay, then what you need to use is feature selection. So you select fewer features. Okay, then your model can be simpler. Okay, and you can also reduce the parameter to fit the data. So that's the general idea about select a meaningful feature. So generally, we also normally say feature is this considered as feature engineering. So you select limited relevant features. Okay, regarding regularization, previously, this is what we learned, L2 regularization, is it? So L2 regularization, then you add some term, is it? You sum off the weight, and then you have the lambda ahead of it, that's what we call, is it? So that's called L2 regularization. And for regular, you can also do L1 regularization. And the L1 regularization, you don't square the weight. You just use absolute value and add off the weight together. Okay. And this says L1 regularization is as all usually yield sparse feature vectors. Okay. And the most feature weights then will be 0 in L1 case. Okay. And it says sparsity can be useful in practice. Is it if you have high dimensional data set with many features, is it that are irrelevant? Is it? And especially the case that we have more irrelevant dimensions than samples, is it? In this case, L1 can be quite useful technique for, so L1 can be used for feature selection. Okay, so it's a quite useful tool to select features. Okay, and it says especially when you have more irrelevant feature than the number of the samples, is it? Then in this case, L1 plays an important role. So when you train your model, so based on all of these rules that we just discussed, it will help better for your model selection. And it says L1 and L2 regularization generally as a penalty against model complexity, is it? And in sklearn, how do we select L1 or L2 is you have that option parameter, and then you just put you want to choose L1 or L2. Okay. And here there is another rule of thumb is if you want to enforce sparsity, okay, it's said more 0 entries, is it? And increasing the regularization stress. So you increase the stress. And when you increase the stress, then you choose lower values for the C. Okay, choose lower values for the C. That's because for our regularization, if you choose a lower, then the C, it's the inverse of the C going to be used as the lambda value. Okay, so that's why it's recommend to choose lower values. When you choose lower, it increase the regularization stress. And what next one says you can also use some algorithm to do feature selection. So one of the feature selection algorithm is called we are going to see. So feature selection, so it's called sequential feature selection algorithm. Okay, for sequential feature selection algorithm, it belongs to greedy search algorithms. So it can be used to reduce initial d-dimensional space to a k-dimensional. Okay, and the motivation behind this is to automatically select a subset of the features most relevant to the problem. And then you check how relevant it is it, and based on the accuracy. And then next time you can try with different features. So you loop through and then you will find the best features. So that's a general idea about sequential feature selection algorithm. Another one is called the sequential backward selection. Okay, so it removes feature from the full feature set. Okay, is that until the new feature subspace contains the desired number. So you take some off that until you find the best fit one. So this is sequential backward selection. And here it gives us the detailed algorithm, and you can take a look after class for the detailed information. And here it also in feature selection algorithm in our sklearn live package, and it says the more feature selection available. Okay, and if you want to know more, and you can reference this website to find the more the sequential selection, the selection algorithms. And another thing we needed to discuss is the random forest as if decision tree previously we discussed. Basically, for both of them, they can also be used for feature selection. Okay, so they will give out your feature importance in sklearn. Okay, so sklearn also provide, so here, like here says, random forest in sklearn. Basically, it already collect the feature importance. So there is a parameter that you can choose to find the feature importance. So that one is called feature importance attribute. Okay, so you can get access that parameter, and then it will output all of the features importance. And then based on that feature importance, and then you can select the most relevant features to do some further training. Okay, so this is regarding in sklearn. Okay, you can also do feature selection. And here it says sklearn also implement selector from model. And this selector from model, so this module can also do feature selection. Okay, and it's based on user specified threshold after you do model fitting. Okay, so this can also be quite useful. It says you can use it in random forest classifier, okay, as a feature selector. Okay, so that's the general idea about data pre-processing. And the third concept in this unit is called cross-validation. Okay, so that we can use it to evaluate our estimates performance. Okay, so what the idea over here is, what does the cross validation mean, the general idea? Okay, the general idea with the cross validation is, for this part we already know. So this is a complete data space, is it? Then we do the split to have the training and the testing. Okay, so that's a general one we already learned. And the cross validation, so we have training part, is it? And then we have testing part, is it? And cross validation, so between those, we add another step. We call it validation. Okay, and how do we add the validation? Is it? And also it's called cross validation. So what does that mean? Okay, so here it shows us the idea. So you have your training data set part, is it? And then you divide it evenly into certain chunks. We call them folds. Okay, so in this case, you have 5 folds of data. Okay, with these 5 folds of data, then you pick one fold. This fold is used for validation. And the other 4 used for training, for regular training. Okay, and then you keep doing this. You're doing this kind of split, certain number of time based on your definition, is it? And you can pick different fold, okay, to do this. And then with all of this result, is it? With all of this result, then you are going to find the best suit parameter. Because with different validation and different folds of training, is it? You will get different optimal parameter. Like in case of weight, you will get different optimized weight, is it? And if we consider all of them together and aggregate them together, then it will ease out, even if there's some unbalanced preference, is it? So after you get this, you kind of average them. Then you can use the picked parameter, then do the testing. Okay, so this is the concept, we call it cross validation. And why is cross? Because you have number of folds. And you are not just going to do one-time validation. You're going to do multiple time of validation. So it's the concept of cross validation. Okay, so that's the idea about data pressing and cross validation. We already discussed. And what next left over is the examples we are going to go over. Okay, then we are done with this unit. So for this KNN example, if you go to our website, you should be found. The name is called KNN Wisconsin, okay, the Jupyter Notebook. In this one, we get the CSV file, is it? And here is a glimpse of the data frame. So it has ID and has different features, is it? And what this part is pretty straightforward. Is it? In case the data has question mark, then you use this negative number to represent it. And then we also drop the ID part because that doesn't, we don't need that. And then after we do that, we have the glimpse of the data, so it's get rid of the ID, is it? And you also assign some specific column of the data to some specific data type. So it's pretty straightforward. Then you will have all of your feature part, is it? All of your data set part. And for the X, it's all of the feature, okay, of the feature part. And of course, we don't need the class part. The class is, it belongs to which class, is it? And then for the Y value, of course, it's the target, it's the classification, it's class 0, class 1, class 2, is it? And over here, what we first did is we call the cross validation, is it? And the cross validation belongs to pre-processing, okay? So in sklearn, you need to import pre-processing, cross validation, and next we also import neighbors, okay, from sklearn. So over here, you're going to do the cross validation, and then you do train and test split. Is it? And after that, we create, this time we use the K nearest neighbor, the KNN model, okay? And then we do our fit, and then we check the accuracy with our testing, is it? And you can see the accuracy can be 97%-ish, okay? So that's the part of our KNN model, how to do the train. And this part, because we later on we are going to discuss, but just give you a glimpse, okay? So you can also get the confusion matrix. So that looks like this. This is basically called a confusion matrix. And this gives you a classification report.
We can't see your screen.
So about the accuracy. Excuse me?
We can't see your screen.
Oh, I forgot to share the screen. Oh. I just talked a lot, but okay, let's now. That's just too bad, yeah. Okay, now you can see my screen. So let's just repeat. Okay, so this time we go over, then how about the previous part? When I discuss the data pre-processing, the cross-validation.
I think before you open Jupyter Notebook, it was fine.
Before I open Jupyter, that's fine. Okay, so you already see that. Okay, that's good. So we don't miss a lot. Okay, with this Jupyter Notebook one, then let's see the example. So we, this example in our course website, KN Wisconsin one, the notebook. So you read the CSV file and get the data frame. So nothing new here, and we can get a glimpse of the data looks like. And then what's next is called replace function. So try to do some data cleaning work. Is it? So question mark, of course, we cannot use it. Is it? So that's why it's a substitute with some number, okay? And we don't need the ID column. Is it? So that's why you drop it. And after you do data cleaning, you can get a glimpse of the data file, so nothing new. And this part is just you assign a new data type for your specific column, for basically over here is a specific feature, okay? And what next is we needed to get all of our features, assign them to the X matrix, is it? So what here is you don't want to include the class, the classification column, so that's why you drop it. But your Y, your target value, is based on the classifications, so that's why you need to take it. Okay, after that, we did the cross-validation this time. Okay, so this time we choose the cross-validation because that can improve our model's performance. And if you want to use cross-validation, you need to import the module, okay? And with the cross-validation, then you do the train test split as what we discussed before. And then you can apply the KNN model and do fit and then find its accuracy. So it's all similar as what we already learned. And this part, later on, we are also going to discuss furthermore in our later chapters about like a confusion matrix, precision, and recall. So anyway, so this example also shows, so confusion matrix and the classification like the precision, recall, F1 score, they are also quite helpful for interpretation of your data. Okay, so, and the next, let's see, what this part does is to try to find the arrows. Okay, so of the arrows is that's between 1 to 40. Okay, to find of the arrows to test. This over here is you specify the number of neighbors. Then you can see how it reflects, is it? Because you remember we discussed KNN, so the number of neighbors you choose does matter, is it? So that's why over here to give you the different number of neighbors, then you try with fit and with predict, and then try to find the arrow, is it? And here it gives us the idea. So this is the number of neighbors. Is it number of neighbors? Of course, when you can see when it's too small, the number of neighbors, then the error rate is quite high, is it? So with you increase the number of neighbors, the error rate drop, is it? But you can also see when the number of neighbors reach a certain level, it doesn't help anymore, is it? So there is a optimum number of neighbors. So when you train your model, you can try, okay, with a different number of neighbor, the parameter you try to see what is the optimal, like what this example did. And what is the next part? The random forest, we already know, we already learned last class, so nothing new here. But over here, what we are going to see how we use random forest to get feature importance, okay? And so over here, you can get off the features, is it? So this is random forest. So with random forest, if you want to get all of the features, that's what the special parameter you need to use with the model. So it's called feature importance, is it? With this feature importance, then you can sort it. Okay, you can sort it. You sort it, and then it will give you the output of the feature importance based on its indices. Okay, this is its column index number, is it? And if you want to know the detail, and basically you can see it gives you quite detailed information, is it, regarding the importance. Give you what the percentage tile it takes in overall the features importance. Is it like for the first one, uniform cell shape? It takes over 30% of the importance, is it? Then in this case, some of the very small number, you see like the mitosis, then you can maybe ignore it when you do your model training, is it? So that's the purpose of over here, what we show is feature importance. And you can use random forest to help you to choose. And this cell you can ignore, but if you're interested, you can study it. It uses quite a comprehensive way to also figure out how to do feature importance. And versus if you use sklearn, it's quite simple. It's just you just call the feature important to give you automatically. Okay. And you can, this is just regarding plotting, and that's a later topic. And with random forest, you can also visualize any single tree, okay, with your random forest. Over here it shows. So if you want to get any single tree, you can plug in a parameter called estimator, is it? Then you specify which tree you want to get its the tree figure, is it? So last class we discussed the pi.plus and the graph visualization, is it? This two package. So the similar idea, it's just you just need to pick out the single tree. Okay, once you pick out single tree, you can see a lot of internal information regarding how it comes up with that result. Okay, so that just shows the idea. And with random forest, here it says you can also use some smaller tree, is it? Because a lot of times that tree may be too large. Then you can decrease the depth of your tree, is it? Don't make your tree too big, too deep, is it? So maximum depth in this case only allows 3. So it only have 3 level of depth, okay? Then your tree will be smaller, so it can give you a better view. So that's the idea about this example, about KNN, okay? And the next example is regarding the data pre-processing. The data pre-processing, the data pre-processing, and let's see, I think we are out of time. Is it? How do I already run over time, is it? So